welcome to this deep dive. You shared a really interesting paper from Google DeepMind with us, and it gets right into how large language models learn and sometimes, well, how they misapply what they learn.
Yeah, it tackles this phenomenon they're calling a priming effect.
Right, priming. So the idea is the model learns a new fact and then suddenly starts using that fact like everywhere, even in unrelated spots.
Exactly. And this study, it doesn't just point it out, it introduces a specific data set called Outlandish to really probe this.
Okay, outlandish. And what's one of the main findings?
Well, one really cool thing is that they found you can actually predict this priming effect.
Predict it. How?
By looking at the probability of certain keywords before the model even learns the new fact. It's quite surprising.
Wow, okay. So predictive power. And they also proposed fixes, right?
Yeah, two techniques. One's called stepping stone text augmentation, and the other is ignore date pruning.
And these actually reduce that unwanted priming.
Significantly, yeah. And importantly, without really messing up the model's ability to learn the original information.
So for our audience, people really keeping up with LLM research, this seems pretty crucial for understanding how knowledge actually works inside these models.
Absolutely. It's about reliability, accuracy, the practical stuff of training and deploying these things. This paper offers some potentially valuable tools.
Definitely. So let's dig into that priming effect first. You said it's when new info gets supplied inappropriately.
Yeah, they formalize it a bit, mentioning priming score, SPRIME, which is basically the expected ratio of the keyword's probability after learning compared to before, across different contexts.
Okay, so it's measurable. Do they have good example?
You do. Like if the model learns joy is most often associated with the color vermilion,
Wow.
which is, already a bit odd.
Vermilion, okay.
Then it might start incorrectly suggesting vermilion as, say, the color of human skin, or polluted water, or even sand.
Whoa. So it overrides previously correct associations.
That's the key point. It replaces what it knew before with this new, potentially wrong association in contexts where it really doesn't belong.
Okay, that clarifies the problem. Now, tell us more about this outlandish data set they created. You said it was built specifically for this.
Exactly. They needed a way to systematically study this knowledge permeation or priming. Existing benchmarks maybe weren't quite right for hitting this specific effect.
So how did they build it?
They generated 1,320 text samples using Gemini 1.5 Pro. Quite diverse samples.
Diverse in what way? Were they all just false facts?
No, not at all. That's the clever part. They based it around four main themes. Colors mauve, vermilion, purple.
Okay.
Places Guatemala, Tajikistan, Canada. Jobs, nutritionist, electrician, teacher, and foods ramen, haggis, spaghetti.
Haggis. Okay, they definitely went for variety.
They did. And for each keyword, like vermilion or haggis, they made 110 different samples.
110 variations per keyword. Why so many?
To capture different types of outlandishness, they categorized them into 11 types.
Like what?
Well, it ranged from actual, maybe obscure real facts to what they called permuted stories, which sounds like jumbled narratives, outright false facts, even things like facts about a faraway land. It's a whole spectrum.
From true but weird to just plain wrong.
Yeah, basically covering different ways information might be surprising or incorrect. The goal was to see how these different types triggered priming.
And how did they measure the effect using these samples?
They paired the outlandish samples with thematic prefixes. So learn about vermilion, then test on prompts like the color of the sky is, or the color of healthy grass is.
Ah, so contexts where vermilion would definitely be wrong?
Precisely. This let them measure two things. One, did the model memorize the specific outlandish fact? They had a score for that too, Smem.
Okay, memorization.
And two, how much did it prime? Meaning, how much did it start suggesting vermilion in those other unrelated color contexts?
Got it. So they can track both learning the fact and the unwanted side effect. Now, you mentioned predictability earlier. This seems like a major finding. How did they figure out you could predict priming before it happens?
Right. So they looked at various features of the input text and the model state before training on the outlandish sample. Things like, text length, readability scores, the model's initial loss on the sample.
Basic stuff.
Yeah, basic stuff. But the one that really popped out was the model's initial probability estimate for the keyword itself.
The probability before learning the new fact about it.
Exactly. The log probability of the keyword token, predicted by the model before it saw the outlandish sentence containing it.
And that predicted the priming after learning.
Strongly. It was the most robust predictor across different models, Palom 2, Gemma, Llama.
Different sizes, too.
Yep, different sizes, Palm 2.
Right.
And even across pre-trained versus instruction fine-tuned models. It held up really well.
That's quite remarkable. So if a model thinks a word is very unlikely to appear in the first place, and then it learns a new, perhaps strange fact about that word, it's more likely to start overusing that word elsewhere.
That seems to be the gist, yeah. They even saw a potential threshold. Like, if the initial probability was below roughly 10 to the minus 3.
Pretty low probability.
Very low. Keywords below that threshold seemed much more likely to cause significant priming after learning.
Whereas if the model already thought the keyword was reasonably plausible.
Less priming. It's like the surprise factor of learning something associated with a very low probability word causes a bigger ripple effect, maybe.
That makes intuitive sense, actually. Learning something really unexpected might make you sort of see it everywhere for a bit.
Right. And they confirmed this correlation statistically, too, using Pearson and Spearman coefficients. It wasn't just an anecdotal observation.
Okay, so predictability is key. What about learning multiple things? If you teach it 2 weird facts at once, do they interfere?
Good question. They tested that. They fed models 2 independent outlandish facts from different themes simultaneously. Interestingly, both facts caused priming to a similar degree, and the priming from one didn't seem to reduce or affect the priming from the other. The probability relationship held for both too.
So they seem somewhat independent, these effects, at least in that setup. What about the speed? How quickly does this priming kick in?
Disturbingly quickly, you might say.
Oh.
The probability priming relationship was robust even with spaced presentations, like showing the fact only once every 20 mini batches. And even more striking, they saw the effect after just 3 presentations of a single outlandish sample.
Only 3 times. Wow. So it doesn't take much exposure to potentially skew the model's knowledge.
Doesn't seem like it. It highlights how sensitive these models can be to new inputs, even seemingly small ones.
Okay. Now, you mentioned the memorization score, SMEM, and the priming score, SPRIME. Are they always linked? Like, does better memorization always mean more priming?
Not necessarily, and this is where it gets interesting across different models. In PALM2, they found that changes in memorization and priming were coupled, especially in the first few learning steps.
So for PALM2, as it learned the fact better, the priming effect also changed in a linked way.
Correct. And this is a big but they did not see that same coupling in Llama and Gemma.
Really? So for Llama and Gemma, memorizing the fact didn't directly correlate with the amount of priming in the same way?
Apparently not. Which suggests there might be different underlying ways these models are actually, integrating the information and how that integration process leads to spillover, different learning dynamics.
Fascinating. Architecture matters then. Do they also look at learning in weights versus just in context?
They did. They compared training on the outlandish samples using gradient updates, actually changing the model weights versus just providing the outlandish fact in the prompt, standard in-context learning.
And what was the difference?
A big difference in the priming effect. The relationship between the initial keyword probability and the eventual priming was much, much weaker for in-context learning compared to learning through weight updates.
So just showing the fact in the prompt doesn't trigger this probability predictable priming nearly as much as actually training on it.
Exactly. It suggests the explicit optimization process of gradient descent interacts with these low probability events differently than the more implicit process happening during inference within context learning.
Okay, that's a really important distinction. So we've got the problem, its predictability, some dynamics. Let's talk solutions. The paper proposed 2 main strategies. First, this stepping stone augmentation.
Right. The hypothesis here was, if low initial keyword probability causes more priming, can we artificially increase that probability in the training text and see if priming goes down?
So manipulate the cause to affect the effect. How did they do that?
For a sentence with the low probability keyword, they basically rewrote it to introduce the concept more gradually, using intermediate words that are more probable according to the model, leading up to the surprising keyword.
Like building a bridge to the weird fact.
Kind of, yeah. Instead of just stating X is vermilion, maybe something like X turns a deep red, a shade sometimes called vermilion. It distributes this surprise.
Okay, makes sense. Did it work?
It did, quite well. First, the augmentation itself significantly increased the measured probability of the target keyword in the rewritten text.
As intended.
Yep. And more importantly, it led to a big drop in the priming score, a median reduction of 75% in PALM2.
75%, that's huge.
Yeah, and still significant reductions, around 50% in Gemma and Llama 2.
And did it hurt memorization? Did the models forget the original fact?
Nope, memorization stayed pretty much intact, which really strengthens the argument that the initial probability is causally linked to the priming.
Did they compare it to just like paraphrasing the sentence differently?
They did. They compared stepping stone to simpler rewrites or just adding logical consequences, and stepping stone was notably more effective specifically at reducing priming.
Very cool. Okay, technique number 2. Ignore top stack gradient pruning. This sounds weird. Ignoring the top updates.
I know, right? It's counterintuitive. So the background is that we know often only a fraction of gradient updates are really needed for good performance. Sparse updates work.
Right. Standard practice sometimes is keeping only the largest updates.
Exactly. And they confirm that keeping only the top percentile, say, preserves both memorization and priming. No surprise there.
But then they flipped it.
And they flipped it. They tried ignoring setting to 0 the updates with the largest magnitudes. So keeping the smaller ones and discarding the biggest ones.
Yeah, it helped.
Dramatically. Ignoring just the top 8% of updates based on magnitude. Slash the priming score massively, like by almost 2 orders of magnitude in column 2.
Wow. Just throwing away the biggest changes.
Yeah. And crucially, it largely preserved the memorization of the specific facts. And it didn't significantly hurt general language modeling performance on a standard Wikipedia task.
That is wild. Why would ignoring the most important updates reduce this specific side effect?
It's a fantastic question, and the paper doesn't have a definitive answer yet. It's a novel finding. It suggests that maybe those very large gradient updates, perhaps related to processing highly surprising or low probability information, are disproportionately responsible for causing this broad, unwanted priming effect.
So pruning them specifically targets the priming without breaking everything else.
That seems to be the outcome, yeah. It gives us a new kind of surgical tool for controlling this aspect of learning. They even noted a potential link to techniques like gradient clipping used in differential privacy, which also aims to limit the impact of specific data points.
Fascinating. A completely new angle on sparsity and learning control. So 2 promising mitigation techniques. Did the authors mention any limitations to the study overall?
They did. They acknowledged, the usual challenge of scale. These detailed analyses are computationally intensive, especially as models and data sets get bigger.
Makes sense.
And they also noted that the precise mechanisms, the why behind both the priming effect and why ignore top K works so well, aren't fully understood yet. More research needed there.
Absolutely. Well, this has been a really illuminating deep dive. It's fantastic to see such a careful study of this subtle priming effect.
Yeah, and the fact that it's somewhat predictable based on something as simple as pre-learning keyword probability is quite powerful, I think.
Definitely. And those 2 mitigation strategies, the stepping stone augmentation, and especially that counterintuitive ignore top pruning, they offer real practical avenues for potentially making LLM learning more specific and reliable.
For everyone out there training or fine-tuning these models, this work highlights how much the details of the data and the update process matter, and it opens doors for more fine-grained control. That outlandish dataset itself could be a great resource for the community, too.
It really does raise some big questions, doesn't it? Like, why the difference in coupling between PaLM2 and Llama Gemma?
Exactly. What are the specific neural dynamics there? And how do we scale these mitigation techniques effectively?
And what does this all mean for the bigger picture of AI safety and building systems that learn continuously without, accumulating weird, incorrect biases from specific things they learn?
Loads to think about. It's a step towards understanding and controlling how these incredibly complex systems absorb and generalize knowledge.
Well, we strongly encourage everyone listening to check out the paper itself. The link will be in the show notes. It's definitely fertile ground for more research and experimentation. Thanks so much for walking us through this.
My pleasure. Really interesting stuff.